And actually, I think the stuff we're going to do here in the beginning, the vector valued functions and space curves, is pretty cool. We're going to get to use some Calc Plot 3D. So you're going to get to use the computers a little bit today and make some plots. So let's pick up where you guys left off on the video. So basically, what a vector valued function is a function where each component of the vector is a function. So basically what we're looking at is a way of writing a parametric equation. We talked a little bit about parametric equations in 11.6. That's all this is, this R of t. A lot of times we'll refer to it as a position vector, especially today, because it'll help us see some of the properties. But all that really is a set of parametric equations in 3 space, an equation for x, y, and z with the parameter t. So it's going to do 2 things. It's going to organize our parametric equation and leverage what we know about vectors. So we're going to go right into having a little bit of fun here, using the Calc Plot 3D. So we're going to start off with something basic. What does the graph of cosine t sine of t look like between 0 and 2 pi? It's a circle. Tell me more about that circle. What's it? Sorry, Dimple? Radius of 1. What else? Where's the circle centered?
At the origin.
At the origin. Okay. Now, obviously, we're in 3D, so we're going to have a third component. So there's our circle. Again, this is, guys, this is right out of trig, right? So here's where it's going to get interesting, is when we add that third component, and we're just going to start off with 0. Now in Calc Plot 3D, here this would be a space. Bless you. Is what we call a space curve. It's basically some kind of line in 3D as opposed to a surface. So if you go to your space curve, you can see cosine and sine are already in there. We're just going to put 0. We already said cosine and sine make a circle centered at the origin of radius 1. Well, we didn't really mention it before because we only were dealing with the xy plane, but it lies in the xy plane. So if we go to plot this guy, there's our circle of radius 1 is sitting in the xy plane, right? If we look straight down, same circle we saw before. So pretty basic idea so far. It's a circle in 3D. We're going to do some cool stuff with that circle though. For instance, what if I change the z coordinate from 0 to 1? What is that going to do to my curve? Yeah, it's like a vertical shift up 1, right? It's going to go up 1, and it's going to hover 1 unit above the xy plane, right? Nothing crazy going on there. All right, let's make it a little bit more interesting. What if we change the z component to t? Now the z component varies. And I see you guys doing it with your hands.
Spring.
Kind of like a spring, right? Or a helix. Yep. All right, let's see what we got. So we change that to t. And we get a helix. Let's change the axes a little bit so that we can see that a little better. Right. We're good on the min and max, but let's make it a little higher and lower. And we can see our helix in there. Let's make that actually a little wider so you can see it a little bit. And there's our helix. Now let's talk about this helix a little bit based off of just what we know. Let me make sure this matches the slide. This is 0, see 2, 5. So if we look at the helix now, let's talk about what we know. Well, it starts here in the XY plane and it starts at 0, 1. Zoom in on that so you can see it a little bit better. And feel free to follow along on your own computers if you like. What is the radius? What do you think the radius of this helix is? It's going to be 1. If we look right down the z-axis, I'll get as close to it as I can. Really what we're going to see is a circle of radius 1. Okay. And notice that it starts at the XY plane and goes just a little bit past 6. What is the height of this helix?
2 pi.
It is 2 pi. Good job, guys. Now, I'm pointing this stuff out for a very specific reason. One of the things I'm going to ask you to do today, and one of the things you'll be asked to do for a take-home problem for the midterm, is to create a helix of given properties. All right. So if I want this helix to have a radius of, let's say, 3, what do you think I need to change in my parametric equations? And think about going from a circle of radius 1 to a circle of radius 3 in trig. What's creating that radius of 1? We saw that changing the z just made it go up. Yeah, Mark.
You put a 3 in front of the cosine and sine.
All right, let's give it a shot. 3 in front of the cosine and sine. And boom, there's our radius of 3. You can see it. If we look down that z-axis, we got a circle radius 3. Another thing I want to point out about this helix, it does one winding, meaning if we look straight down, again, I'm sorry, a little hard for me to get it perfect, but you see how it starts here and ends here. So it does one winding, and that's because we're going through 2 pi radians, right? It takes 2 pi for sine and cosine to get through their period or to go around a circle. So we know how to mess with the radius. What if we wanted it to also have a height? Let's see, our height is about 2 pi. What if we wanted it to have a height of 10 exactly? What would we have to, first off, which equation or equations would we have to adjust the height? We'd have to adjust the z, right? And right now the z is equal to t, so it goes from 0 up to 2 pi.
So it's like missing the limits, basically.
We got 2 options, and this is going to be important. Option number 1 is we can mess with the limits on our interval because it's going from 0 to 2 pi because t goes from 0 to 2 pi. But if we do mess with those, that messes with our number of windings as well, which is fine. Guys, for the curves that you make in parametric equations, there's an infinite amount of ways to do it, literally, because changing the parameter, you can also change the equations and vice versa. I'm going to show you one way, but changing the parameter works just fine too. So we have a radius of 3. Let's say we want a height of 10. Right now, the height is 2 pi. Well, let's think of it in terms of actually, I'll go here. We know that, so actually we'll call it z. Z is equal to some parameter times t. If we find that a, that's going to be our coefficient. Well, if we start at 0, we're fine. We want it to end at 10. So then we know that when this thing is at 2 windings, t is at 2 pi. So a times 2 pi. Well, we want a to be such that when we're at 2 pi for t at 2 pi radians, that this equals 10. We just solve that for a. So a equals 10 over 2 pi, or 10 over pi. Sorry, 5 over pi. Does that make sense? Again, we could have adjusted the limits as well, no problem. But then we would have to mess with the inputs of sine and cosine, the periods, because because we want to make sure we still get one winding. So this is a real easy, this is one way of doing it, and let's make sure that it works. So we're going to do 5 over pi times t. And if we look, let me see, I got to zoom out now. We see that this thing ends exactly at 10 and does the 2 windings. Now, maybe one winding. Let's say we wanted to do 2 windings, but still have it end at 10, right? Well, if I do it up to 4 pi, that gives me the second winding, but right now it's going way higher than 10. So we just need to make an adjustment here. And 2 times pi. And there it is. There's our helix that has a radius of 3. It does 2 windings and a height of exactly 10. Okay. Like I said, you're going to get a chance to try one of these in the worksheet, but I really wanted to point out that, you know, I'm not guessing on how to get it close to 10 because we can make it actually end at 10. I'm not guessing on the number of windings because I went from 0 to 4 pi. But let me show you another option. If I wanted to have the, remember I told you there's an infinite amount of ways to do this. If I cut the interval in half, but then I put 2 here. Notice now I'm getting the 2 windings, but now it's only half as high because I cut the height in half on the z. So now we can get rid of the 2, and there's the exact same graph we just had. Different parametric equations, different t interval. So anytime you're doing a space curve, make sure you include your t interval because that's what's going to determine where it starts and where it ends. All right? Questions about that? I just want to take some time to kind of point out how those pieces work together, the windings, the radius, and the height. Because like I said, you know, you're going to do one on the worksheet today, and there will be one on the midterm take-home problems. They're not hard as long as you know what you're attending to. And those are the 3 things that you want to look at. We'll get a little playtime today too to see how it goes. Too nice is going. So there's our helix. All right. Another one here. I added a t in front of the sine and the cosine now. What is that going to do? It's going to make it get wider as t gets bigger, right? So let's see. Let's go back to a little bit more basic. T, we won't worry about height for right now. We know how to do that. And 0 to 2 pi. Okay. Oops, I didn't mean to put those guys on for later. All right. This is still a helix. This is what we call a conical helix because it's the shape of a cone. Oh, and I left the 2 t's in there, which is fine. It's just going to do 2 windings. Now, it's a little harder to tell the number of windings on a conical helix versus a regular helix because it's getting wider, but the same principle applies. For every 2 pi that sine and cosine go through, you're doing another winding. Adjusting the height is the same as doing the helix that we just did. And these things have a radius too. What is currently the radius of this helix? What size circle does it make here at the big end? Any idea? What's that? Sorry, I couldn't hear you, Jumbo. It's going to be based on t, and since t is ending at 2 pi, 2 pi, you got it. So if we wanted to have a certain size radius, we could do the same thing we did last time. So let's say we want a radius of 10. we would do the same thing on these guys, 5 divided by pi. 5 divided by pi. And I don't quite have the graph out long enough for us to see that, but see if we're going to 2 pi. Yeah. So because if we're going up to 2 pi on this one, we know that 2 pi times 5 pi over 10 is going to give us 10. So we're going to end at 10. So again, we're not, I just want to point out, we're not guessing on those numbers. We can find them out nice and exact. So like I said, I'm only going to have you do one of the ones on the worksheet for today just to get some practice. There's 2 of them on there. I just want you to get used to messing around with the coefficients, seeing what it does to the graph, putting it in a space curve. All right. So that's our conical helix. So that's the stuff, that's basically what I wanted to talk to you about with space curves. We'll use these more actually in the very next section. So we're going to see these again. But you're going to plot one here once we break into groups. We'll go through 12.2 first. Last thing I want to talk to you about in 12.1, I'm not going to take a long time on this. We may look at limits of vector valued functions. And when we do those limits, basically you're just calculating the limit of each component. So it's basically like 3 Calc 1 problems. All right. And so remember to calculate a limit at a point. First thing you do is plug it in. If you get a number, you're done. If you get 0 over a number, you're done. If you get a number over 0, it's undefined. And then if you get 0 over 0, it's an indeterminate form. You have to use some more techniques like graphing, factoring, or L'Hopital's rule. Okay. And we might see L'Hopital's rule this semester. You're not allowed to forget that one yet. The reason we bring this up is this brings up our definition of continuity for a vector value function. It is the exact same definition of continuity you saw in Calc 1, which is that not only does the limit exist, it's also equal to the function value at that point. It's just with the vector value function, it has to be done for all 3 components. That's all. So it is literally like doing a Calc 1 problem 3 times. We'll get one to practice one of those today too.
Question.
Yeah.
Can you have like one, like just Z be like discontinuous, but like
Once one of them is, that's what this last line even says right here. It's they all have to be continuous for the vector value function to be continuous. So yeah, if you, let's say you do the first limit for x of t, if it's not continuous, you don't even have to check the other ones. We know the limit doesn't exist. That's a good point. I'm glad you brought that up because we're looking at continuity. Well, if one of those pieces fails, then the whole thing fails. Other questions? All right. Well, now we've seen limits, so we have officially, finally, in week 3, done some calculus. Took a while. Now it's going to get even more fun. Derivatives and antiderivatives of vector valued functions. I'm still going to be using Calc Plot 3D on some of this because it's pretty cool. We can look at. Let me see. So for you guys at home, if you're not able to see the screen that well, make sure you're following on the PowerPoint. I know I've got it up there, so hopefully you can see it. All right, so we've got these vector value functions, and I mentioned that we'll call that R of t the position vector, because we're going to start in a very similar place to where you started Calc 1, and that is the relationship between position, velocity, and acceleration, because of all the very nice properties that come out of it. So this guy here is our position function, which again, like we said, basically that means that each component is just given as a function, which could be a constant, but doesn't have to be. But they'll all rely on some single variable, in this case, t. So here is our vector valued function, and let me bring that up. That's what this looks like. Let's see, we're doing 0 to 4 pi, so let's match that up. We know that it makes a helix, right? So 0 to 4 pi. It's got a height of just a little bit over 12. It's got a radius of 10. So you don't need that far negative on the z. So let's get some of that off. Okay. So there's our helix, right? This is exactly what we just looked at last time. What we're going to do is kind of look at some of the properties that are pretty cool. Okay. So what I want you to imagine this is the path that a bug is moving or a particle, and it's going to go move along this helix, right? So we know it has a radius of 10, 2 windings, and it goes up the z-axis. And our position vector is going to be in whatever units our axes are in, feet, inches. It's some linear distance. That's one of those things, the things about the space curve. It's a linear curve in 3 space. All right, so it's kind of like the edge of the room, not the floor of the room. So it's just one dimension. All right. Now, one of the nice, we'll use feet just because I want to talk about units a little bit, but centimeters, anything would work. So after we talk about position in Calc 1, we talk about instantaneous velocity. Remind me, if we have a position function, how do we find the instantaneous velocity? The derivative, right? So for a vector valued function, all we do is find the derivative of each component. So once again, guys, that's what's cool about the stuff we're doing today. It is really all Calc 1 stuff, just put into a vector and plotted in 3D. So we're going to be doing some derivatives today. So if we had the position function we had before, then our velocity vector would be -10 sine t, -10 cosine t, 1. All right, nothing crazy going on there. That's just taking 3 derivatives. Now, one of the things we want to talk about is the difference between speed and velocity. Velocity is a vector valued quantity, meaning it has direction and magnitude. The magnitude of velocity is speed. Okay?
The magnitude of velocity is speed.
You got it. So the magnitude of velocity is speed. So make sure you differentiate between those two. Velocity is a vector valued quantity. Speed is a scalar. It is literally the magnitude of your vector, of your velocity vector. So we can actually calculate the speed of our helix. You know, it's the same magnitude we were using last time. And the velocity vector is going to be tangent to the object's path. So we'll put those on in a second, I think. Let's see. Let's put on our velocity vector. Not that one. All right. So here's our plot. Oh, there we go. And you see that black vector right there? That's our velocity vector. I'm going to take off that blue one just to make sure it's not too confusing. It's the trace vector. It basically goes from the origin to the point, but we don't really need that right now. This is our velocity vector. Notice how it's always tangent to the path of motion. All right, we're going to look at something real cool here. So we've got a velocity vector. We're just going to do this one together. We've got a velocity vector of 10 cosine t, 10 sine t, sorry, -10 sine t, 10 cosine t, 1. So if I'm looking at the magnitude of v, it's going to be the square root of -10 sine t squared plus 10 cosine t squared plus 1 squared. Okay. Some really cool stuff happens here. So square root of 100 sine squared t plus 100 cosine squared t, and 1 squared is just 1. Perfect. Is everybody seeing the Pythagorean identity in there? Basically, sine squared plus cosine squared is 1. So if we factor out the 100, we'd have 100 times 1. And so this comes out to be square root of 101. And units we're doing is feet per second. Now there's something really cool to notice about this, and I'm gonna point it out in the plot as well. Notice that our magnitude does not depend on t. It could have, depending on what, depending on, this just happened to work out real nice for us. But this does not depend on t, which means that our speed is constant. But our velocity is not. So let's go back to Calc Plot 3D and make sense of this. All right. Watch what's happening, and then you'll see it a little better if I look straight down this thing. All right, what do you notice about the length of that velocity vector?
It is not changing.
It is not changing, right? Which is exactly what it means to have a constant magnitude, or in this case, a constant speed. But what is changing on that vector?
Direction.
The direction, which is why velocity is not constant, but the speed is. Again, making just that differentiation between the two, right? So, I mean, it's really cool to we can actually see this happening, right? That vector is not changing size. I didn't even put in a space curve for that vector. This is actually pre-built into Calc Plot 3D. So we have a changing velocity. Well, let me see. I might have these not in the order that I thought I did. So let's talk a little bit about direction, then we'll come back to the changing velocity. All right, nothing new here. We've already talked about, the position vector and the velocity vector. Well, then the direction is basically the unit vector of the velocity. Because what's that doing? That's taking away the magnitude and talking about the direction of that vector that was going around the helix. This is called the unit tangent vector. Let's think about this for just a second. What did we do to find it? Well, we took the derivative. Well, that's how we find the slope of a tangent. And now in this case, because it was vector valued, we turned it into a unit vector, and that's what creates the unit tangent vector. So it's that first derivative of your vector valued function. And then if you normalize it, right, if you divide by the magnitude, it becomes a unit tangent vector. And again, like we talked about before, when you have a unit vector, that preserves direction while getting rid of magnitude, hence the name unit tangent vector or direction. All right. Now, one last thing we got to talk about, and then we are going to do some, okay, maybe a couple last things we're going to talk about. All right, going back to this guy. We said this velocity is changing even though the speed is not. What is the name of the force that changes velocity? If you have a change in velocity, what do you have?
Acceleration.
You have acceleration. How is acceleration related to velocity? It's the derivative. So putting together what's great about this is we're just leveraging what you guys already learned in Calc 1. The acceleration vector is the derivative of the velocity vector, which is the derivative of the position vector. So this is our acceleration vector. now we can add this to our plot here. And I think it really does a good job of kind of showing how it works. I know you can't see it just yet, but you will. It's that green one. Notice how the velocity vector, or excuse me, the acceleration vector is pointing perpendicular to the velocity vector. Right? And if we look straight down, or as straight down as I can get it, please. We can see. Now, let's think about why this makes sense in terms of vectors. If the acceleration vector had any piece of a component in the direction of the velocity, then the magnitude of the velocity would be increasing. So it cannot be either in the direction or opposite direction of the velocity, because that would change the speed, right? Think of speeding up or slowing down. So it has to be perfectly perpendicular because we have a constant speed. Because all it's doing is changing the direction. We can see that real clearly on this drawing. See how it points towards the center at all times as we go around our helix? Because all it's doing is changing the direction. So a lot of cool properties. And again, it comes from stuff that you guys have already done. It's just now we're looking at it as a vector valued function. Oh, lost my dots on the dot product, unfortunately. But, you know, these are just a couple properties for doing the dot product of vector. You would dot u dot v, if you're doing the derivative, excuse me, of the dot product. I mean, you can always do the dot product and then take the derivative too. So this is just a couple properties for the dot and the cross product. I don't want you to worry about those too much. Those aren't going to come up very often.
So it's just product.
Pretty much. Yep.
Okay.
That's exactly what it is. And it's a simplified way if you're taking derivative of a product of two vector value functions or two, the cross product of two vector value functions. But yeah, notice how the setup is pretty much like the product rule, except up here, obviously it's dot for dot and cross for cross. We're not going to do that, but I want to go on just last thing we're going to talk about antiderivatives of vector value functions. Well, hey, we just saw taking derivatives of vector value functions. We can go the other direction too. For instance, if we have a velocity vector and we want to recover the position vector, we would do the antiderivative. So you're just doing the antiderivative of each component. Now, if we do not have an initial condition, we do have to still observe the plus c because we have a general antiderivative. But you can just put a plus c with a hat on it, and that's representing a constant vector at the end. Or you can put a c on each component, that'd be fine too. Just use, if you do a c for each component, make sure it's like C1, C2, or C3, or A, B, C, because they can all be different values. And last thing is we can have definite intervals of vector value functions. That would be if we're trying to get some kind of net change in the vector value function, distance traveled, or depending on what what we're taking the integral of. All those properties that you learned in Calc 1 still hold. And so you would just do 3 definite intervals. So like I said, we're going to get to do some calculus today, but as of right now, it's just going to be the same calculus you did in Calc 1. We're just doing it on vector valued functions. So you got it. Questions at this point? Let's work some problems.